Now, chapter one's a little bit all over the place. We're going to talk about sets and set builder notation. We're going to talk about intervals, graphing intervals. We're going to talk about parent functions and transformations. We're going to talk about matrices. We're going to talk about systems of equations. We're going to talk about a little bit of everything in chapter one. Chapter one's a little bit all over the place. It's the last chapter and the only chapter that's going to be so many different topics. Like in geometry, chapter one's a lot of different topics. Algebra one, a little bit of everything. But once we get past chapter one, chapter two, we're going to focus on parabolas. Actually, that's what the chapter is called, focus on parabola. And then start focusing on specific topics. Now, first thing we're going to talk about is sets, a set. Now, a set is a collection of objects. We normally use braces around whatever the list of set is, or a set's members. So we use braces and put the set's members inside the braces. So a set is just a collection of objects. That's all a set is. You can have a set of darts, a set of cards, a set of numbers. It is just a group or a collection of objects. So we do have this set 1, 2, 3. So we put a brace, 1, 2, 3, brace. And that's it. That's the set containing the elements 1, 2, 3. An element is a number in the set, or an object that is a part of that set. Each object is an element. So would we say listing the set 1, 2, 3 is pretty nice, easy to do? We can do that. Let's look at the next one. Positive even integers. What is the smallest positive even integer? Do we know? 0. 0. 0 is actually the smallest, not integers, positive even number. Smallest positive even number is, well, really we wouldn't say 0. Yes, 2 is actually the right one. I've been saying 0 all day. I don't know why. Because, Angel, you are right. It is 2. It's not 0. Y'all know why? 0 is not positive or negative. So technically it would be 2. I've been spacing on that all day. So if you had listed 0, I would have taken it. It's not technically correct. It would be 2, but we have that there. Might as well just remove it. You don't have to. 2 would be the starting one. But are we actually able to list all of them? No, because it's going to continue on indefinitely forever. So we put the ... Now, there are ways to write it more accurately. That's where we're going to get into set builder notation. We're going to talk about that tomorrow. But this here is our positive even numbers. We good with this here so far? Okay. Now, one of the ways that we can start writing, especially in set builder notation, is we need to describe the types of numbers. Now, the first set of numbers that we have are natural numbers. So in that box, inside of the box, that one there, natural numbers. Yep, right there. In that box in the center, because we're going to start building this out. Natural numbers are naturally the numbers you count on your hands and your feet. Because really what we're doing, if you write a number line, you need to write it above it. 1, 2, 3, 4. This gives us really our counting numbers, our positive numbers going to the right, if we're looking at a number line. 1, 2, 3, 4, 5. Because these here are our natural numbers. Okay. Now, in a lot of ways, especially I consider, and some would too, mathematicians have a tendency to be a little lazy. If we can write something simpler, more to the point, condensed, we're going to do it. So instead of writing natural numbers each time, especially in proofs, they give it this symbol here, an N with two lines. So when you see this, especially in proofs, and we start talking in higher level math, they will use this here, this symbol, this N with two lines, instead of writing out natural numbers every single time. So this is considered, or see this here, we're talking about natural numbers. That's what that N is. And these are our natural numbers. So we go with natural numbers. Yes? The next set of numbers that we have is called the whole numbers. All whole numbers are, so our natural numbers, all the natural numbers are whole numbers. But not all the whole numbers are natural numbers. What is the only thing that whole numbers adds to this? 0. 0 is a whole number. 0 is not a natural number. So the only thing whole numbers adds is 0. 0. Whole numbers. Anybody have a guess at what our symbol for whole numbers is? Kind of a trick question. Natural numbers is N, whole numbers is? They don't have one. But yes, normally when I talk about it, we'll call it W, but they don't actually give a symbol for whole numbers. Because since the only thing it really adds is 0, instead of talking about the whole numbers, we're actually going to talk about the integers. Integers adds negatives. Because we'll talk about, especially if we want 0 and above, we would say that we're looking at the set of non-negative integers. The non-negative integers. Instead of talking about whole numbers, we just say non-negative integers. So this is starting to give us our negative numbers. So -1, -2, -3, -4 going on is our integers. And as we start doing this, hopefully you start seeing that we're starting to add more and more numbers to this number line. We're starting to find all the numbers on the number line, our whole group. Natural numbers N, we call the whole numbers our W. Integers is obviously, yes, Q. Or, let's see here. No. My brain decided to take a walkabout. Yep, it did. I'm sorry. Twice in 1 hour. Got to get some myself. I got ahead of myself. Integers is Z. Rational is Q. I knew as soon as I wrote that, I'm like, I think I'm putting one ahead. Integers is Z. Integers is Z. And it's not because we're not wanting to use I with 2 lines. I is already taken. Because historically, we always do stuff in a set pattern. When something comes up, something's discovered, we give it definitions, we give it symbols, and then move forward. If something else comes up later, we have to give, even if it was like integers, another term that had an I, well, the I with 2 lines already been taken. We've got to give it something else. The other thought that I have, especially earlier today, there's a good chance we refer back to the Latin or the Greek roots of the word. Okay? This is kind of a segment off on this tangent. Slope. What's the letter we use for slope? M, yes? Has anybody else wondered why we don't use S for slope? Slope, S, M. It's because, again, going back to Latin and Greek, to talk about a rise and inclination is montagne, where we get our word for mountain is a rise, montagne, M. slope. So again, it sometimes comes from the origin of the word. So here we have z, positive, negatives. We good with this so far, yes? Next one, this is where our Q does come in, is our rational numbers. These are any number that can be written as a fraction. Any number that can be written as a fraction has a terminating decimal is our rational number. So now we're starting to fill in some of the numbers between 0 and 1, 1 and 2, -1, -2. We are getting these numbers between our integer numbers. So 0.5, 6/5, 1/4, 0.25 and 1/4 are the exact same thing. We call these numbers rational number ratio, comparing two numbers to each other. They are a ratio. Questions on this here? But we also have numbers that are not rational, and we call them irrational numbers. Because a number, like the number 3, is a natural number. It's also a whole number. It's also an integer. It's also rational. 3 is not irrational. Specifically, irrational numbers, I'll scroll up, are numbers that cannot be written as a fraction and have a non-repeating, non-terminating 0. Now, the first one that I listed as an example, you don't have to write the whole decimal number, just to get the idea, is pi. We use pi especially for circles, finding area of circles, and types of rotation, 3.1415926, and it keeps going on. The one below it is phi. Phi is considered to be the golden ratio. If you look at especially Greek architecture and Greek sculptures, they love phi. Phi shows up everywhere. It is this arcing, it is a arc or a curving arc that expands out in this kind of perfect symmetrical pattern. If I remember, I think it's like 1/4, 1/8, 1/16, 1/32. It does continue to expand out in this kind of nice, pretty pattern. Phi itself is not a nice number, but it does work very well. And the last one here is E. E is another irrational number. It's non-repeating, non-terminating. And we use it for logarithms, logarithmic equations. We won't look at that till the spring. It's going to be a few months before we look at logarithms. Okay? So we kind of see these here. Now, these are not the only irrational numbers. Square root of 2 is irrational. Any radical that does not reduce is going to be irrational. The cubed root of 2, the 8th root of 2, the 16th root of 14. These are all different irrational numbers. We have lots of irrational numbers. That there is our I with 2 lines. But that also means we probably had the concept of an irrational number before we had the concept of a integer. Yep. I with 2 lines is irrational. Irrational numbers, because again, we did have a concept of irrational numbers before we had negatives. The Greeks did have the concept of an irrational number, the concept of pi, and this kind of proportion. They did not have an exact value. It was pretty darn close, but they were able to kind of get it figured out, especially in that era. And then we have the last set here, and that is the real number system. And the symbol for the real number system is a R with 2 lines. It contains irrational, rational, whole numbers, integers, natural numbers. All of them are all the real numbers. Now that does beg the question. If we say there's such thing as real numbers, that must mean what? Yes, there are imaginary numbers. And we call them the complex numbers. The imaginary numbers, complex numbers, because complex number is parts real and parts imaginary. It's a little complex. And we will talk about complex numbers, especially once we start hitting chapter 3 and 4, about these non-real numbers. But until then, we're not going to worry about them. We'll put them off to the side. Now, we use these especially to define numbers and define sets to help us better describe a set of numbers that is not easily to describe or easily to define. Because there's ways, especially with set builder notation, like our positive even numbers, where we can define them and not have to list a ton of numbers out. That, even though even numbers we can set a pattern, we're good, because there are going to be some sets that are not easily describable, easily that we can write down. We have to have another way to do it. Because the best way I could say it is, especially in kind of real world terms, is if we said that we want to list out the set of all Colcord High School graduates. How many would want to write that out? Because again, I did not set a timeline at this point. That means you'd have to list out everybody that graduated last year, all the way, I think, to 1925, 1920, 1919, or somewhere close to there. It would take forever. Wouldn't literally take forever, but it would take quite a while to do it. It's not feasible to actually write it out. So there are ways, especially with numbers, we have set builder notation to do it where we don't have to list it out, and especially where there's not a set pattern where we can repeat. So that's where a set builder notation is going to be nice. But here, the set of whole numbers less than 10. This one, we will start at 0, because 0 is the smallest whole number, yes? Our next whole number would be 1, then 2, 3, 4, 5, 6, 7, 8, 9. Since it said less than 10, that's it. It's easy to do. We can list those out. It's not bad. How about the set of odd whole numbers less than 24? So a set of odd whole numbers, so the smallest odd whole number would be 1, then 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23. Because 0 cannot be positive or negative, but it is even. So the smallest odd number is indeed 1. Questions on these here? Are we kind of good with sets, writing a set? Yes? So from here, we're going to talk about something called a subset. A subset is a set that is a part of a larger set. Now again, with some of these definitions, you can write them verbatim, word for word, or if you can think of it in your own terms or think of it a way that you understand better, go for it. Because a set is a part of a larger set. It's when all members of set A are also contained in set B. When all members of one are contained in the other, it is considered a subset. So for us here, this room, my classroom, we can say is a subset of the high school, yes? Every part of this classroom is contained in the high school. We could also say that Colcord High School is a subset of Colcord, Oklahoma, yes? Colcord High School is also a subset of the state of Oklahoma. Yes, we can keep going out further and further. Can we say that the high school is a subset of this classroom? No, there's definitely parts of the high school that are not contained in this room, yes? Okay. Now looking at these two sets, can we say that set A is a subset of set B? Yes. So there's two ways we can do this. One is we can write out set A is a subset of set B. Mathematically, a mathematician would not write that. They would, but they wouldn't. Again, mathematicians have a tendency to be lazy. We're going to write it this way. That symbol in the middle means subset. We're saying that set A is a subset of set B. That's how we'd read that. Because everything in A is contained in B. Can we say this next statement? B is a subset of A. No, because there are elements of B, specifically 100, that is not contained in A, yes? So we have to change this statement a little bit. Draw a line through it. Because just like with our equal sign, we drew a line through it, we said it was not equal. Here we're saying it's not a subset. B is not a subset of A.
Teacher, may I have your attention, please? Any cheerleader who ordered a skirt needs to go see Miss Six Keller. Doing great. Thank you.
My next question is this here. Can we say that set A is a subset of set A? Because what is the definition of subset? Everything in one set has to be a part of the other set. Is everything in set A contained in set A? Yeah, so A is a subset of A. Can we say B is a subset of B? Yeah. We can say a set is a subset of itself. That's perfectly fine. Now, we're going to take this, as I would say, above and beyond. At some point, especially hopefully for the math classes you've taken, you've had at least one teacher say you cannot write a 0 with a line through it. Yes? Hopefully. Because 0 with a line through it, this here, is not 0, especially when we talk about sets. This is the symbol for the empty set, the set containing nothing. So our set containing the empty set, can we say that it is a subset of set A? So can we say that the set containing nothing is a subset of this set A? It does contain something, but could it be a subset of nothing? Could a subset of nothing be part of A? Oh yeah. If a way that I think, especially I've been using today, if we think of this classroom, if we took everything out, literally took everything out of this room, would it still be a part of the high school? Yeah, so this is still a part of set A. Even if it contains nothing, it can still be a subset of A. The empty set can be a subset of any set. That can be a dangerous trail to follow. Because, and the reason I say that, can we also say the set containing the set that contains the empty set be a subset of A? Well, yeah, because it's just a set containing the set that contains the empty set. Are y'all starting to see how this can get? We can keep getting more and more. We could say that it's also a subset of the set containing the set containing the set that contains the empty set is a subset of A. But again, it's just an empty set. It's a set containing an empty set, or the set containing a set containing an empty set. Again, it's true, it works. It's one of those things we understand it but don't understand it at the same time. But again, as I said, above and beyond. Last thing before we move on to the next page. This example here, is A a subset of B? Well, set A is what? AB. Set B is ABC. So we can say this is true. Is B a subset of A? No. And we could say that A is a subset of A, B is a subset of B. We can say that's true. All right? Questions on this here? Next thing we're going to do is we are going to list, we're going to write some subsets. specifically non-empty subsets. Because the thing we just did a minute ago was empty set of an empty set of an empty set, we're removing that from the board. We just want to see our non-empty subsets. And we want to write out every non-empty subset. This is a little bit easier than you might think, or not easier, but you'll see it once we start doing it. Because again, a subset is a set that contains part of the whole. Anything in a subset has to be in the main set, yes? So if we look at the first one, 4, 5, one of our subsets could be the number, or set containing the number 4, because this here, the set containing 4, is a subset of the set 4, 5. Yes? What's another one? The set containing 5 would be a subset, yes? There's one more. The set containing 4 and 5, 4, 5, would be a subset of the set 4, 5. Those are all the subsets. We have every subset for the set 4, 5. We ready to look at the set CD? Okay, so what would our subsets be? C, subset, so set C, set D, and then the set CD. Yep. If we have 2 elements, we're going to have 3 subsets. Yeah, if you're struggling to write those braces, that's fine. That's I think the way that it helped them to write it is to write an S and then a backwards S. Yeah. It takes a while to do it, and even after doing it for so many years, none of mine look the exact same. You're good. Questions on A or D, A or B? So 2, 4, 6. 2, 4, 6. Let's look at the subsets for it. So let's start with the individual subsets first. So we could have what? 2. And then 4. And then 6. Okay, cool. But we could also have sets that contain how many elements? 2. So what's one that we could have? 2, 4. We could also have 2, 6. Yes, I'm getting ahead of myself. 2, 6. And then lastly, we could have 4, 6. Because we could have 2, 4, 2, 6, 4, 6. And the order in which we write them doesn't matter. We just need all 3 listed. Now for us, for all intents and purposes, 2, 4 and 4, 2 are the same set. For these here, order is not going to matter. There are some sets where order does matter, where the order of how things are written does make a difference. Okay, but for here, order doesn't matter. 2, 6, 6, 2 are the same thing. Do we have any other subsets? 2, 4, 6. So it's kind of interesting, when we had a set containing 2 elements, we had 3 subsets. We went to 3 elements, now we have 7. So I wonder what's going to happen when we have 4 elements. Well, first one's the easiest ones to start with. For E, set containing E, set containing F, set containing G, and then the set containing H. Because those are all of our 1-element subsets. But we could also have 2, yes? So what's the first one we could have? EF. Then we could have EG. And then EH. Is that all the 2 elements? No, we could also have what? FG. And then FH. And lastly, we have GH. So those are indeed all the two element subsets, yes? Is that all the subsets? We could also have 3, E, F, G. Now once we start getting multiple, the way that I keep track of them and make sure I get them all, for like 3, I will keep the first 2 letters the same. And we'll look at the third. This way. I think that's better for y'all to see, yes? So EF will keep the same, because we could have EFG, but we could also have what? EF, EFH. And we'll keep putting that last letter, keep going out to the right, because EFG, EFH, okay, there's no letter after H, yes? So that means we could change the second letter from F to G, which would mean that we have EGH, because that's just the 2 letters after it, yes? Because we wouldn't use EGF, we already have it. Can we move any letter after H? Any other elements after it? Nope. So EGH is the last one there. We can't move G over to the next one, but can we move E over one? So E would become F, G, H, yes? Can't move H over, there's none after H. Can't move the G over, F over. We have all of our 3s, yes? Now where we finish with the subsets. We got to do the whole thing. E, F, G, H. 1, 2, so 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, yeah. I will tell you this, you will not have to write these braces after this chapter.
Me too.
So that's kind of interesting that we've added one more and it jumped from 7 subsets to 15. You ready to do 6? No? Okay. Nope, that's it. We're only doing 4. We're not going to do 5 or 6 because, again, the more elements we add, the bigger the number of subsets that we have. Now, the next thing we're going to look at with subsets is above and beyond. I say above and beyond because it's just taking it a step further. You won't see this, most likely won't see this on a test. But it is, again, we're applying this concept of subsets. And again, this is a part of mathematics. I did cover this in college. It was the very first lesson, or one of the first lessons I had with intermediate algebra. Yeah, there it is. Yeah, intermediate algebra. So, number line. We know the number line. We talked about it. You don't have to write this. I would not write it under intervals. This is extra. So the number line, we know what that is. All the real numbers, yes? Yeah. Now, mathematically, we call the number line R1, the real numbers, first dimension, first degree. Now, normally we talk about this especially as the x-axis, yes? Well, we also have, especially started talking in Algebra 1, we add the y-axis. We have the xy coordinate plane, yes? 2 dimensions. So we call this R2. Is the xy coordinate plane or is the x coordinate plane a subset of the xy? Yeah, because everything contained on the x-axis is a part of the xy. We can agree with that there, yes? We see it. A 2-dimensional plane. We don't live in a 2-dimensional plane. We live in a 3. X, Y, Z. Which means that we can say, that the R2 is a part of R3. And we can keep going. Now, there is no homework assignment yet. When we finish it, we will have a homework assignment.